Okay, I'm just going to repeat myself, sorry, just so that it goes up on the video. So we're talking about radian measure, and the angle that is 1 radian is equivalent to having an arc length of 1 radius. So if the arc length is 1 radius, then we have an angle of 1 measure. Oh, and don't point at the board, point here. So this formula is the formula we were working with yesterday. The ratio of arc length to circumference is the same as the ratio of sector angle to the angle around the whole circle. So the arc length is 1 radius, the circumference is 2 pi r, the angle is 1 radian, all the way around the circle is 360 degrees, and if we simplify that, we get pi radians equals 180 degrees. So that's not going to be a very good explanation for the video, because that's the 3rd time I've said it today, and I keep forgetting to record it. Okay? But now, we'll have the real lesson. All right, so we're going to convert these. And as we convert, I want you to think about how we're converting, but also we want to start memorizing these. So we want to be able to say what 90 degrees is in radians without having to do the conversion in our head, with just knowing what it is. And it won't happen today, but we'll get there. So if pi radians is 180 degrees, then how many radians is 90 degrees? So if 180 degrees is pi, then 90 degrees is half a pi, right? So we say pi by 2. It just means pi divided by 2, but it's the short form of how we say it. So if 90 degrees is pi by 2, then 30 degrees is pi by 6. Yeah. Because we're going to divide this by 3. So if 90 is pi by 2, then 45 is pi by 4. Okay? If 180 is pi, then 60 is pi by 3. Very good. You're getting this. Okay, if 90 is pi by 2, then 270 is 3 pi over 2. And if 180 degrees is pi, then 360 degrees is 2 pi. Okay? Okay, so those ones you should start memorizing, because we'll use them all the time. Notice that they're your special angles, 30, 45, and 60, but also 90 and 270 and 360 are important to us because they're the axes on the coordinate plane. So we need to convert from radians to degrees and from degrees to radians. And on your sheet looks exactly like my sheet, only I've added these little arrows because converting from radians to degrees, this is the correct conversion factor, but the examples that go with it are down here, because these are radians that we're going to want to convert to degrees. And then here, converting to degrees to radians, this is the correct conversion factor, but the examples that go with it are up here, because these are degrees, and we're going to want to convert to radians. Okay? Notice that when we want to convert from radians into degrees, we want to end up with degrees, so we have degrees on top. When we want to convert from degrees to radians, we want to get rid of degrees, so we want the degrees on the bottom so that they'll cancel out. Okay? Notice also that if I just give you a number like this, and we're talking about angles, how do I know if that is degrees or radians? How do I know that that 2.5 has to be radians? There's no degree sign. So if I'm talking about angles and there's a little degree sign, we are dealing with degrees. If there's no little degree sign, then we're dealing with radians. Okay, and radians can be written like this, or they can be written in terms of pi. So usually when you see the pi, that's a dead giveaway that it's radians, but this is radians as well. Okay? All right, so we're going to take our radian measure, these three, and we're going to convert them into degrees, and we're going to use this conversion factor. So in other words, we're going to multiply by 180 degrees over pi. Okay? notice when we do that, the pi's here, whoops, not there, the pi's here and here divide out. And so what we get is 4 over 3 times 180 degrees. So it's exactly the same as if I had just taken that 180 degrees and substituted it in there for pi, because pi is the same as 180. Yay! So that's a shortcut. When there's a pi there and we're going to convert into degrees, we can just change the pi to be 180 degrees and then work it out. So 3 goes into 180, leaves you 60, and 4 times 60 is 240 degrees. Whoops, 240 degrees. Okay? So let's do this one with that shortcut method. We want to change negative 13 pi by 9 into degrees. So instead of using the conversion factor, we're just going to stick, instead of a pi, 180 degrees. And what do you get? You can put it in your calculator, or you can do in your head. 9 goes into 180 20 times, and negative 13 times 20 is negative 260 degrees. Okay? Everybody okay with that? Okay. Now, in this example, when there's no pi in the example, we can't use the shortcut. We have to use the conversion factor. So we have to multiply by 180 degrees divided by pi. And we just put it into our calculator, 2.5 times 180 divided by pi, and you get out of it, what? Sorry, 143, right? 0.24, whatever it is. Okay, everybody okay with that? Now, when we're converting from degrees into radians, we do exactly the same thing, only we multiply by pi over 180 instead of 180 over pi. So we're going to multiply by pi divided by 180 degrees. Okay? Now, your calculator will simplify this fraction for you very easily. If we want to write it in terms of pi, we want to simplify 75 over 180. So if you put it in your calculator, 75 divided by 180, then hit the math button. So don't hit enter, hit math. The very first choice there is changing it into fraction. So hit enter and hit enter again, and it will give you the reduced fraction. So what is 75 over 180 reduced to be? 5 over 12. And so we get 5 pi over 12. Okay? So that's a nice feature of your calculator, that it'll do fractions for you and reduce fractions and so on. But I could very easily ask this question on a non-calculator question, as I'm going to do for this one. So let's say this one is without a calculator. We're going to convert negative 210 degrees into radians. So you're going to multiply by pi over 180 degrees. Do it without a calculator. Now, that is the exact value of negative 210 degrees in radians. Okay? But I could also ask you to round that to 2 decimal places. So if you were going to give me the answer rounded to 2 decimal places, obviously I couldn't ask you that as a non-calculator question, but as a calculator question, you would just put into your calculator negative 7 times pi divided by 6 and round to 2 decimal places, and I believe it's negative 3.66. Sorry, 667? Okay. So it's negative 3.67, and now that's the approximate value of negative 210 degrees in radians, and that's the exact value of negative 210 degrees in radians. Okay? We all right with that? Okay, so we are going to spend the rest of the time doing exactly the same things that we did on Monday in degrees, but we're going to do them in radians. So you can see how they work exactly the same way, but you have to think about the pi's and the angles and those kinds of things. Okay? But let's first discuss arc length as promised and see how that's different. Yeah?
Okay, for the last one you said that you dot marks if it was -7/6 times pi, like
Oh, like if you wrote it like this, -7/6 times pi?
yeah.
No, I'm okay with that. As long as it's clear that the pi is not in the denominator, that would be fine. Okay? Okay, arc length. So if you recall yesterday when you developed your formula for arc length, okay, you said that the ratio of the arc divided by the circumference was the same as the ratio of the angle divided by the full angle for the whole circle. So the only difference between this and what you were doing yesterday is that instead of 360 degrees down here, you've got 2 pi radians. Okay? Because 2 pi is the same as 360 degrees. Now, 2 pi, if you notice, cancels from the bottom of both of these. So we have a over r equals theta, or a equals r theta. And so that is lovely and easy to remember, but you can only use it like that if theta is measured in radians. Okay? If theta is not measured in radians, then you can use your conversion to change the radians into degrees by multiplying by 180 degrees over pi. And that's the exact formula that you had yesterday. Right? And I wrote it the wrong way around. I wrote it the wrong way around here. Because I have radians. No, I didn't write it the wrong way around. I have radians, and I want to change it into degrees. So I wrote it the wrong way around here, I guess. I feel like I didn't. I'll have to think about that. Because I'm recording, so I don't want to stop for too long here. Okay, so let's use our formula where a equals r theta when theta is measured in radians to calculate here x, where x is your arc length, and here x, where x is your angle. So go ahead and try those. Okay, so what are we getting for the arc length for A? Arc length is r theta, right, which is 10 times 1.7, so we should have 17. And the sector angle here, what are you getting for that? Alfred? 1.5, yeah, or 3 over 2. Here, x is our angle, so our angle is a over r, which is 6 over 4, which is 3 over 2, or 1.5. Either one. Okay? Any questions so far? Okay, so over the page, I don't have the second page scanned for whatever reason. But we're still going to talk about what you've got on your second page, okay? So with angles in standard position, it works exactly the same way for radian measure as it does for degrees. You've got initial arm, you've got terminal arm. The hardest part for radian measure is remembering or being able to identify which quadrant you are in, okay? If I give you a particular angle. So if I give you an angle like pi by 3, what quadrant is pi by 3 in? So 1/3 of pi, what quadrant will that be in? First quadrant, okay? It's first quadrant. And if I give you pi by 4, what quadrant are we in? It's also in the first quadrant. So how do we make sense of that? Recall that this is 0 degrees, and it's also 0 radians. And then all the way around to here is how many radians? It's pi radians, right. 180 degrees is the same as pi radians. So if that's pi, then this is, what's this? Pi over 2. Yes, Seamus, you finally understand my clock now. Except that the time is wrong. But anyways, so then it's pi by 2, it's pi. All the way around here is 2 pi. And what do we get right here? What do we get right here? It's 1 pi by 2, 2 pi by 2, 3 pi by 2. Okay? So what about pi by 6? Where is pi by 6? First quadrant. Because it's less than half a pi, but it's more than nothing, right? What about 4 pi by 5? What quadrant is 4 pi by 5? Quadrant 2, because 4/5 of a pi is more than half a pi, but it's less than 1 pi, so it has to be in quadrant 2. Okay? What about 5 pi by 6? Also second quadrant. What about 7 pi by 6? Because that's 1 pi by 6 more than a full pi, right? What about 11 pi by 6? And how do you know that, Seamus? The clock. Okay, so 4 pi by 6 is in the second quadrant. Now, it's hard to just do that in your head because you're trying to compare fractions. And it's easier to compare fractions if they have, just put it on my desk, Joel, thank you. If they have a common denominator. So if we're trying to figure out where is 11 pi by 6, if we changed all these to have a denominator of 6, so 3 pi by 6, which is the same as half a pi, 6 pi by 6, which is the same as a full pi, and you can't see the 6 on the screen, sorry. And here I would have 9 pi by 6, and here I would have 12 pi by 6. Now when I tell you 11 pi by 6, you can see that 11 is more than 9 but less than 12, so it must be in quadrant 4. Okay? So having a common denominator on your axes can be helpful in determining which quadrant you want to end up in, and it can be helpful in determining your reference angles, which you're going to have to be able to do in a little bit too. Okay? Okay. Any questions about that piece? So, coterminal angles. Coterminal angles work exactly the same way in radian measure as they do in degree measure. If we have an angle like 110 degrees, what quadrant is 110 degrees, Joel? I know, put the phone away. You need to be paying attention. You've been away for so long. 110 degrees is in which quadrant? Walker? 110. Here is how many degrees? And here is how many degrees? So what's this angle here? Walker. 90. And if I go all the way around to here, it's... So 110 degrees is in the first quadrant?
110.
Yeah, 110 degrees. I'm asking you, which quadrant is 110 degrees?
But 400 degrees.
Oh, I'm not doing 400 degrees. I'm doing 110 degrees. Sorry. Second quadrant. Yeah, sorry if that was confusing. And if I wanted to find coterminal angles to 110 degrees, what do I have to do? What do I do, Rita, to find coterminal angles? Yeah, and any multiple of 360 is going to do, right? Now, if I have an angle that's in radians, let's say I have 3 pi by 4, and I want to add to get coterminal angles. What do I add to get coterminal angles when I'm in radians? 2 pi n. And normally we write 2n pi. Is more traditional to stick the n in before the pi. I don't know why. But you'll see that in your textbook more often, 2n pi. Okay? Where n is an integer so that we are adding and subtracting multiples of 360 because n can be positive or negative numbers. Okay? So now let's try it for 400 degrees. Okay? First of all, which quadrant is 400 degrees in? first quadrant, okay? Because it's 360 all the way around, plus another 40 would put me in the first quadrant, okay? So for us, we want to add multiples of 360 to this. And so give me one angle that's coterminal with 400 degrees. Seamus? Okay. So can you find 3 more angles that are coterminal with 400 degrees? There's an infinite number of possibilities. You just need to come up with 3. See what you can do. Give me another angle that's coterminal with 400. Shay, what have you got?
40 degrees.
40 degrees. Good. How'd you get that? Subtracted 360. So those are the 2 that are closest to 400. But I want 2 more. Kirsten, you got another one? 1,120 degrees. And you got that by adding another 360 to that, right? Anybody got another one? Negative 320, which we get by subtracting 360 from that, okay? So finding coterminal angles in degrees isn't that hard. Add or subtract multiples of 360. It's not that hard with radians either. You're adding and subtracting multiples of 2 pi. But in order to add and subtract fractions, what do you need? So the common denominator here is 6. So you want to add and subtract 12 pi by 6. So if you've got negative 5 pi by 6, and you add 12 pi by 6, what do you get, Echo? A little bit louder for me. 24. We're going to take negative 5 pi by 6, and we're going to add 12 pi by 6. 7 pi by 6. Yeah, so that's one possible answer. Okay? And we can keep adding 12 pi by 6 to that. So if we add 12 pi by 6 again, what will we get, Yuzuki?
19 pi per 6.
Okay, so there's another possibility there. Or we can subtract 12 pi by 6. So what's negative 5 pi by 6? Subtract 12 pi by 6. Yoshi? Negative 5 pi by 6, subtract 12 pi by 6. Negative 17 pi by 6. And we could subtract again, or we could add to this. There's infinite possibilities. Okay, if we subtract again, we get negative 29 pi by 6. If we add, we get 31 pi by 6, etc. Okay? We all right with that? All right, the last little blurb on this sheet is reference angles. Reference angles work the same in radians as they do in degrees. I'm going to keep saying that. It's the same. They're always positive. They're always acute, less than 90 degrees, and they're always measured to the nearest x-axis. Okay? Now, you are pretty good at finding reference angles with degrees, so I'm not going to do these 2 examples with you. But let's do the 2 examples that are in radian measure. So the negative 4 pi by 3 and the positive 11 pi by 6. Okay? In order to find reference angles, we need to know what quadrant are we in, and then we can determine what the reference angle is. Okay? And to find the quadrant that we're in, it's easiest if all of our axes are in thirds. Okay? Have denominator 3. It's easier to compare. So we start with 0. Up here, this is pi by 2. But if I convert that to a denominator of 3, I have to multiply by, any ideas? 1.5. Right? 1.5 times 2 is 3. So I've got to multiply that by 1.5 as well. Okay? So I mean, it's not beautiful. It's like very ugly. But it's not, this isn't like your answer. This is just to help you get to the answer. This is a guide for you and you alone. Over here, this is normally pi. So we're going to change it to 3 pi by 3. Okay. And then over here, this is normally 3 pi by 2. We're going to multiply top and bottom by 1.5 again, so we get 4.5 pi over 1.5. And this is 2 pi. We're going to multiply top and bottom by 3. We get 6 pi over 3. So these are what we're using as our guides to help us figure out where is negative 4 pi by 3. Now, of course, negative makes it a little trickier. Negative means that it's going in this direction. So if I'm going in this direction, which quadrant am I going to end up in if I'm going to turn negative 4 pi by 3 times? Which quadrant will I end up in? Where will my terminal arm be? Quadrant 3 here? Why? Yeah, it actually goes around more than full pi, doesn't it? But the thing is, it's going negative. So it's going in this direction. So it's going here. This is negative 1.5 pi by 3. And this is negative 3 pi by 3. So negative 4 pi by 3 is actually in here. It's actually in second quadrant. Okay, negative is harder because we labeled everything in positive angles. Okay, so negative 4 pi by 3 is here. Okay, second quadrant. But what is the reference angle? What is this angle right here? That's what I'm asking you for. So we went around this way. We went a full pi around here. So that's 3 pi by 3 in the negative direction. And this is 4 pi by 3 in the negative direction. So the difference between those two is pi by 3. So the reference angle here is pi by 3. Okay? Try it for 11 pi by 6. It's positive, which makes it a little easier. Label your axes in terms of denominator 6. We end up in fourth quadrant. Because we're at 0, we're at 3 pi by 6, we're at 6 pi by 6, we're at 9 pi by 6, we're at 12 pi by 6, 11 pi by 6 is almost all the way to 12 pi by 6. That reference angle is the difference between 12 pi by 6 and 11 pi by 6, so the reference angle is pi by 6. Right? Well done.